Carl Kadie. He leads the Fast LLM open source Python project for genomics. He also contributes to other Python and Rust projects, including a visualizer for the Turing machine, bbcchallenge.org website. Previously, Carl was a principal applied scientist at Microsoft and Microsoft Research, where he worked in machine learning, statistics, and genomics with publications in Science and Nature. Carl will be performing his talk here, so Q&A will be at the end. I'll be facilitating, so if you've got a question, go ahead and raise your hand and I'll walk over to you with the microphone so that we can have that recorded in the image, in the recording back there. So once again, Carl Kadie, it's a pleasure.
Thank you. Good morning. Today I'm going to be talking about a little side project I was working on to answer a question that just I wanted the answer to, but it also infuriated me. And that's, why can we solve some equations easily while others seem impossible? To answer this properly, you need probably a graduate degree in math, which I don't have. So we're going to do a PyData kind of solution. We're going to cheat and use a Python project called SymPy to get some heuristics. I think all the introduction stuff was already mentioned about me. I should say this isn't my main work, but when I do get motivated to do something, I'll spend some time trying to figure it out. So mathematical models are very important to those of us doing data science. Sometimes that's just in the sense of a mathematical equation. So if we fit some data, now we think that our output is equal to our input squared, then we know that means that if we have a 3 going in, we'll get a 9 out. Sometimes we'd like to run this backwards. We'd like to take our machine and shove the 9 in and see what number comes out. And we hope we'll get the 3. From school, we know how to find the backwards machine. If y equals x squared, then we apply square root to both sides of the equation. Square root of x squared turns into x. Square root of y is plus or minus square root of y. And we get this nice equation. Interestingly now, when we shove the 9 in, we'll get both a 3 and a minus 3 out. We'll have to figure out which of those is meaningful, if perhaps only one is. Here's another equation. If I shove 1.471 into this equation, my computer has no trouble telling me the answer is 0.603. But what if I want to jam the 603 in and see what I could have put in to get the result? Well, we'll do what we did before. We'll write y equals x, this constant sine x, and then I have no idea what to do next. So what I really want here is a nice equation, what's sometimes called a closed form formula. We'll see that sometimes we can find a closed form for these inverse solutions, and sometimes we can't. When we can't, if you ask somebody, they'll say, well, you can use numerical methods. We'll talk about that. What I wanted to know is, when can I expect to find these closed form solutions, and when can't I? And then maybe I won't really answer this, but why doesn't anyone teach us this? Why aren't we taught what we can solve and what we can't? Let me define what I mean by closed form solution. I mean some formula with a finite combination of standard operations. And standard operations here are going to be things like plus, minus, divide, sine, cosine, arctan, log, exponent, things like that. If you can get that, it's super nice. If you can't get that, we do have these great numerical methods that could get you your answer to as many decimal places as you want, usually pretty efficiently via some fast but iterative computation. And we'll see in many cases this is perfectly practical, but if we can get the closed form, we prefer that. So to find out when you can get the closed form, you can do it 2 ways. You can do it rigorously using things like Galois, if I'm pronouncing that right, theory, which if you're a math major, you might see in your junior or senior year in college, undergrad math. Or for some of these other equations we'll look at, you need to go into transcendental number theory or algebraic geometry classes that even a math major probably wouldn't get until they're a grad student. I'm not a mathematician, so we're going to use SymPy, which is a free computer algebra system for Python. And we're just going to try a bunch of stuff. We're going to try polynomials, exponentials, logarithms, and trigonometry functions and see what we can observe.
Yeah.
The most famous equation is the one I started at the beginning. This is an equation from 1609 from Kepler related to the orbit of comets. The equation just says that y equals x minus c sine x. X is the position of the comet along the orbit. So if my head is the sun, then closest to the sun is angle 0. As far away as it'll get from the sun is angle 180. Halfway there is angle 90. 270. Usually we'll express these angles in terms of radians instead of angles, instead of degrees, but it's the same thing. The constant c tells us how round the orbit is. So if the thing is going perfectly round, that has a c constant of 0. If it's a comet that's coming way up and down, almost straight down, then that'll be 0.99 something. Y is the time. So if the comet has a period of 76 years to go all the way around, then we'll say when it's a quarter of, then we'll say 19 years, we'll call that 90 degrees, because that's a quarter of 76. And we'll call 36 years 180 degrees, and all the way around 76 degrees. So imagine you're Kepler's research programmer when you have access to Python, and Kepler asks you, when will the comet go a quarter of the way around its orbit? What time will it reach that quarter way mark? So you would get your Python out. You can use NumPy. You just define his equation like so. We've already established for this comet what the eccentricity is. Put these in, print, and you get the answer. It'll take 7.3 Earth years for the comet to move from 0 to a quarter of the way around its orbit. So that's a good answer. It's kind of interesting. It means it's reached 25% of its path in just 10% of its total orbital time. So that's because it's moving really fast when it's close to the sun, and it slows down when it gets farther away.
Bye-bye.
But now, no good deed goes unpunished. Now Kepler wants you to answer a problem going the other way around. How far in radians will the comet have traveled along its orbit after 20 years? And you go, okay, 20 years is 10/19 pi of its total orbit. We set up our equation, and we can tell that we have the equation x minus this constant sine x minus 10/19 pi equals 0. We want to know when x, we want values where x will make this, we want to solve for x, which means finding where this will be 0. We can plot it and see that the answer is somewhere around 2.3, and the Python code to do that is straightforward. Reading off from a plot is a little annoying, and we're only getting like 2 digits of precision. So we might ask SymPy, this computer algebra system, to solve this for us. Set up the same things. We use sim.solve, asking it to solve the equation, and we're going to get an error. It's going to say not implemented, multiple generators, no algorithms are implemented to solve this equation. So it looks like we're out of luck. Happily, if we just need an answer, we can change sim.solve to sim.insolve and get a numerical solution. And when we run this, it'll say, after 20 years, the comet will have traveled 2.3 radians, which is 134 degrees along its orbit. So we've gotten our numeric answer. And we can fill in a row of a table, just help keeping track of what we've learned so far. So for this particular equation, when we tried to find a closed form solution, we couldn't, and we got a particular error. We were able to find a numeric solution. There might be multiple ones, but these numeric methods will typically only find one for you. And here's our numeric solution out to 4 decimal places. So let's fill out the rest of the table, starting with polynomials. Polynomial is an expression, for example, x squared minus x minus 1 equals 0. Is probably the most fundamental family of equations for mathematical modeling. We describe a polynomial by the highest exponent in the equation. So degree 2 is called a quadratic. If the highest exponent is a 3 or a 4, that's of course more complicated. In fact, in Renaissance Italy, mathematicians would challenge each other to find the solutions to 3rd and 4th degree polynomials. And if they eventually worked out procedures so they could always find the closed form answer to 3rd and 4th degree polynomials. But they got stuck on 5th degree. Sometimes they could find a solution and sometimes they couldn't. So what does SymPy say when we put these in? Well, for one with the square, we learned how to do that in school, right? That's just using the quadratic equation. We get these 2 solutions. The next example has a cube in it. The answer looks really complicated, but it's all in terms of division and subtraction and square roots. We'll talk a little bit more about that one. Sometimes I said that the Italian Renaissance people couldn't solve the 5th degree ones, but sometimes you can. So here's one where there is a solution and SymPy could find it. But here's another one and SymPy can't solve it. Instead, it gives us some error message talking about C root of. But in all the cases, we can get a numeric solution. Some observations. Below closed, from degree 4 and below, we always can find a closed form. It uses basic arithmetic operators and things like roots. We often get multiple solutions, but the number of those solutions is never more than the degree of the polynomial. Looking at row 2, something that's kind of annoying is it's got that I in it. That's the square root of -1. So it's a complex number. In a lot of our applications, getting an answer with a complex number is no answer at all. So we might get an answer and then decide it isn't applicable to our domain. In 1832, Galway did some proofs showing that polynomials of degree 5 and higher generally can't be solved, but of course sometimes they can. We've seen SymPy confirming that. Here's an example of the thing I said we had to watch out for, which is these complex solutions. If I ask you to find the solution to x squared plus 1 equals 0, we can do the plot. We can look at where the plot crosses 0. It doesn't cross 0. So in that sense, there are no solutions. But even from the quadratic equation that we learned in high school, we'll get 2 solutions. It's just that the solutions will be -I and I. So they are solutions, but they're solutions that may be meaningless in our domain. This is so important. It's called this is part of the fundamental theorem of algebra from Gauss around 1800. And that says that for any polynomial, there will be solutions, but maybe complex solutions, and the number of solutions will be equal to the highest degree of the degree of the polynomial. Okay, that's our polynomials. Let's move on to what happens when we have exponents and logs along with some expression of x. So that would be like x e to the x, x plus e to the x, x log x, x plus log x, and so on. On the first row, you can see sometimes we can just get lucky and there'll just be a simple answer. The other rows, SymPy is showing us answers, but it's showing us answers in terms of this function called w, which I had never heard of. Has anyone seen w before? It's showing up all over here. So in a sense, these are solvable, closed form, if W is allowed. But what's W, and should we allow it? So W is a function first defined by Lambert in 1758. Interestingly, it wasn't until 1990 that it was formalized and kind of defined and named in a concrete standard way, and that was by another computer algebra system. It's defined as the inverse of x exponent x e to the x. It can give you multiple answers, but so can square root. It won't give you more than square root can, so that's okay. Like square root and log and arctangent, it's well-defined and easily computable. So if you ask me, I went from never having even heard of the W function, and now I'm the W function's strongest advocate that we should definitely count it as part of what counts as being in closed form. I should say that if we're mixing exponent and log with some polynomial thing, we can still trip up with things like fifth degree polynomials and beyond and complex solutions. So this doesn't solve everything, but it does seem to solve a lot of our problems with exponent and log. What if we have an expression that has an exponent part and a log part? So e to the x log x, or e to the x plus log x. SymPy says we can't solve it. And as far as I can tell, we can't get a nice closed form solution if we're mixing these. But we can still get a numeric solution, no problem. So you can look at how complicated these equations are. I'm calling this trigonometric simple because it's simple to ask. If we just have sine x plus cosine x or times or whatever and put this into SymPy, we'll get these answers out. They're very big, but they're still made up of things that count as closed form, arctangents and roots. We can see there's some i's in there, some complex numbers, so that could be annoying. But in general, in all these cases, where the input to the trigonometric function is the same or just offset from each other, we're going to, at least according to SymPy, we're going to get answers. But what if the input in one is x, like it's sine x, but it's sine plus sine of 3x? So now we can, trigonometric terms, that's different frequencies. When we do that, sometimes we'll get solutions. If they're there, SymPy seems pretty good at finding them. Some of these kind of have a hidden problem that to solve them, you'd have to solve a 6th degree polynomial, which we're not going to be able to do. Some of them have a different problem. You can see the red graph there, which is the last row from the table. Its problem is it doesn't cross 0. So in that sense, there's no solution. And in this case, it's not that there's no solution. We'll give you a complex solution that you can ignore. In this case, there's no solution, and it's just not going to give you any thing at all. I did try a different computer algebra system called, SymPy on some of these just times out. And then it's like, well, I don't know. I'm going to assume that if it was easy to find, it would find. But maybe it's not. Wolfram, which is a different computer algebra system, it's proprietary, but you can use it to some degree for free on the web, does a slightly better job than SymPy at solving some of these, but some of them just aren't solvable, apparently. And the worst case for trigonometry, if the input to our equations are different values, so or values that are multiples of each other, so like x and square root of 3 of x, that means their frequencies aren't even comparable. It's still, of course, always possible to just construct something and be lucky and be able to get a solution. But generally, these aren't solvable. Sometimes there is a numeric solution, but look at the two graphs here. They come very close to 0, but they don't quite touch. And from that, we can see that there's no solution. When we ask SymPy, our numeric method, to give us the numeric solution, it's going to give us a value error. So there's no solution at all. And the worst thing we can do is put together the trigonometric functions with something like these polynomials or exponents and logs. Almost anything you do with a trigonometric function connected to something from any of these other families is going to fail to get a closed form solution. Although often we can, if there is one, we can often find the numeric solution efficiently. So let me give you a cheat sheet. If you give me something with a 5th degree or above polynomial, I'm going to say it's probably it's solvable. The reason is the degree is too high. If you give me something with an exponent or a log, but just 1, I'm going to say, well, it's unsolvable if you don't allow w, but you should allow w. If it's mixing exponent and log together, then it's probably not solvable. The sines and cosines, they're usually solvable if the inputs are multiples of each other, but not always. And if they're different frequencies, the inputs aren't integer multiples of each other, then they're probably not going to be solvable at all. And the worst thing you can do is do what Kepler did, which was take a trigonometric function and then add it to a polynomial or one of these other families. Let me finish up with 2 things here. Let me just talk about what surprised me while working on this project. One is I was very surprised and happy at how simple Kepler's equation was. I didn't know that something that concise could represent something as complicated as the way a comet orbits and speeds up and slows down. As I mentioned, I'd never heard of Lambert's W function, and now I'm like its strongest advocate. I've been a fan of SymPy for a while. I gave a talk a couple years ago about understanding physics using SymPy by making a physics engine that didn't do any approximations, that kept everything exactly precise. So that was not only fun to watch like little circles collide with each other, but it even had philosophical implications. So anytime you need to do algebra or calculus, or you think it might be useful, be sure to look at SymPy as a free possible way to help you out there. I know now not to expect trigonometric functions to be solvable, except in the kind of the simplest case. And this reiterated something that I kind of already knew, that when a closed form solution is impossible, we still have plotting and numerical methods that'll often give us a practical result. So thank you for joining me on this journey. Let me talk about a few of the resources. This is based on an article in Towards Data Science in Medium called Exploring Solvable and Unsolvable Equations in Python. There's a GitHub repository, and you can see all the examples, including things that print out the pretty typeset tables in Python notebooks. I mentioned the game physics thing. If you like kind of what can you do with a computer algebra system now that it's easy to program in Python, you can look at the article for that. I think that has a link to the talk. And let me give credit to what got me started on this tangent, and that was an excellent video by Welsh Lab on YouTube called Kepler's Impossible Equation. So thanks. And
thank you, Carl. And again, if we've got any questions, I'm happy to facilitate here. I will bring the microphone over to you.
When it comes to starting to go into numerical methods and you start to kind of get into that realm, and you can't really get a closed form solution, is there anything that you've done so far you could see doing in the maybe the probabilistic realm, right? Maybe like using some Bayesian methods, things along those lines to start to approximate what those values should be. And
let me think. So I should know about Bayesian methods. I was in a decision theory group and we were required to be Bayesians. I think the main takeaway for numerical methods is don't forget to do the graph if it's at all possible, so you at least have some idea of what it is you're talking about. In these cases, we're looking for exact solutions. Some of the things like in the keynote talk today, they were trying to find the best line that would fit the curve. In this case, we're trying to find the only line or the only equation that exactly fits the data. So that's a little bit difference in here. At least at this level, we're not trying to think of how we should penalize inaccuracies and noise, although in many, many domains, that's of course super important.
Hello, hello. In one of your slides, you had a timeouts.
Yes.
Can you comment on how long was the timeout? Did you time out yourself or the SymPy timed out?
SymPy actually said timeout.
Okay. Do you think that would
I'm
be
pretty sure.
Do you think that would be CPU related, or was it mostly that it wasn't converging and that's his way?
I don't know. Those are some of those examples were ones where Wolfram gave a more definitive answer, even if it didn't come up with, even if there was no closed form solution, Wolfram was at least a little bit more definitive about that there was a problem going on. I think some of the SymPy things are stochastic algorithms. And I think sometimes they don't know how long it will take to find an answer, and then they do just give up. But maybe if it looked 1 second longer, it would have found it.
Also, semi-related, I saw the not implemented errors for some of those, and are those specifically related to gaps in implementation, or are those for things that are not solvable?
I don't. So we know because people look at the Kepler equation that some things are like known to be not solvable, but it's really, really hard to. No, I don't even think that's true. I don't even know that the Kepler thing is known to be non-solvable, even though people have focused their attention on it. So this is a situation where we don't know what we don't know. They have some procedures that either deterministically or stochastically will solve some things, but there are other families of equations that nobody knows if they're solvable in closed form. And of course, we throw in a W or some other new useful function, we can be redefining a little bit by what we mean by closed form.
Yeah, follow up on the timeout error question. For the closed form and numeric solutions, was there a lot of variance in runtime? Like, what was runtime like for some of these different families of functions?
Yeah, that's a funny question. In all these cases, the numeric stuff runs really well. It's pretty much, I mean, my rule of thumb is even if it's having to do a loop to get more and more precise answers, it's often getting like one more decimal place of precision or more every time it loops. So, okay, it has to loop 10 times to get you 10 decimal places. Well, 10 times is fine. On the other hand, you could see some of the things on the trigonometry where it got an answer. The answer was this big, and I didn't even show you there were multiple answers. So say there were 10, and each one is huge, and they're all giant nested expressions. Just allocating the memory for that is going to take more time than the numeric method's going to spend to do its 10 little loops. So I would imagine that many times the numeric is faster than the closed form symbolic. The difference maybe is when you got the symbolic, now you can run it on anything you want, and it should have a predictable speed. The numeric, you've got to redo the numeric stuff for every particular set of inputs that you want.
I was going to ask, have you looked at PySR and symbolic regression approaches that kind of try and search through the space of possible symbols to get equations?
No, I don't know what PySR is. What is it?
It kind of just does a breadth first search over a bunch of equations. And I think one of the motivating use cases was discovering Kepler's laws from just Tyrone.
Oh, from the data.
Yeah, just from the data.
Yeah, that's a little, in the domain, that's a little different. That's what Kepler did before he gave the problem to us to put backwards. It would be funny to take that and try to give it all the data in reverse and ask it if it could come up with a solution directly for the inverse, but we're pretty sure it wouldn't be able to do that. It should be able to find Kepler's equation going forward. I mean, ideally, hopefully it will.
I wanted to ask, so you said if it's a 4th degree polynomial, it's solvable, right?
Yes.
I am not sure if I'm going to say this right, but I think like for a lot of these, like for the trigonometric functions, there's Taylor series expansion, which expresses it in terms of a polynomial, assuming you can compute the derivative, which is pretty well behaved for trigonometric functions. And I know it's like the more terms you add, the more precise you get. In what cases would the first 4 terms be sufficient? I feel like it'd be a decent amount, right?
Yeah, let me address that in 2 ways. So for a lot of well-known functions, most of the trigonometric functions, there's an infinite formula that you can use to get the answer to as many decimal places as you need. It's called a form of that is the Taylor expansion. That doesn't count as closed form because the number of terms is infinite. But as pointed out, if you only need it to 10 decimal places, some of the Taylor things will double the number of decimal places you get with every term that you add. So if it goes 2, 4, 8, 16, well, how many do you need? And in those cases, 4 is probably going to be enough. I don't know how to characterize it generally, although I think they do error analysis on Taylor series. So I think they have got, it's understood. It's just not understood by me. Any more?
Any further questions? So we got one in the back.
Hi, I noticed that a lot of the equations that you were saying would be unsolvable with the different models that you're using tend to have graphs that don't cross the x-axis. So I'm curious from a physics and like a thermodynamics standpoint, we use a lot of closed systems and isolated systems in that. So I'm curious if the main issue around creating models is not knowing which variables to isolate, or what causes them to be unsolvable if it's not a translation issue.
Yeah, I don't know how to answer that. So let me answer a different question. In a lot of domains, if you're just doing like simple Newtonian physics, and you want to know when 2 things are going to collide, you'll get an equation that'll always tell you when they collide. This is like 2 circles moving in a straight line, even if they never collide. And that solution will be a complex, well, it can be unmeaningful in 2 different ways. Sometimes it'll tell you, oh, they could have collided in the past, even though maybe they were never set up that way. Other times, like 2 balls moving in 2D, like literally will never collide. But you can solve the like simple Newton's equations here, and you'll get a solution, but it'll be complex. It's like, I don't know what that means. But my understanding is that in some physics domains, like electrical engineering, probably some other ones even in mechanics, those complex solutions are meaningful. So I think you have to go case by case in that to decide whether or not, even when that doesn't cross the 0, maybe there's still something meaningful in the complex domain. There's probably some other way to plot it, but I don't know that.